Good morning.
Morning. Sorry, I was on mute.
Oh, no, you're good. It's hard to tell with the Zoom, like who's in, what's listening. Can everyone
Yes.
hear you? Perfect.
Yeah.
I'm sorry. I'm leaving the doctor's appointment, so I'll be listening for a little bit. I'm sorry.
No, that's totally fine. And the recording's available to you later if you need it.
Polyprotic acids. Oh no. Here it comes.
There's a word for that. We know that word.
Is it? Do we
I
really
think,
know this word?
yeah. You learned it in 110. It means more than one proton.
I don't think I could do that. Oh, it was a question on a homework, and then um something about mono atoms or di or tri, whatever,
Correct.
and you have
So
to like
anything
figure out.
anything that's not mono is polyprotic. So H2SO4, H3PO4.
Oh, okay. Makes sense. How many people from 110 is in this class?
So I think I have 10 students at the moment.
Is that?
Yeah.
Oh,
We never have as
perfect.
many in 111 as we do in 110. It's just not as required for as many majors. So
Makes sense. Why is everybody taking this class? Just for funsies?
I, I doubt that very much. Most people need it either for medical school or PA school or something along those lines.
I don't know. I find this immensely interesting for some odd reason. Like there's a lot of a lot of interesting information, and like it makes me think about other subjects from a different perspective. It's kind of cool.
That that's kind of the point. That's why we make you take it.
It's like I feel like 110 was very like on the surface, but like this one
Yes.
sometimes it gets a little more in depth.
Oh, that's very true. That is very true.
Like I think like that whole I was looking at the review for the rate of the reactions, and like I feel like it was
Yes.
like last week, and I already forgot all about.
Well, that's bad because it's going to be on the first test. So that's bad.
I know. So I'm gonna I'm gonna have to study today again. I'm like seriously, well maybe because I was at I'm like trying to like basically multitask. So I was like sitting here waiting for because they tell you the appointment is at 9 o'clock, and then it's 9:30. They're finally like, oh, the doctor will see you here. And you're like, no, you're supposed to see me 30 minutes ago. You know?
Yeah, I know how that works. Unfortunately, I'm very familiar with that.
It's like, and that's an eye one. I can't see anything without this contacts. So like I'm
Yeah.
like, I need to go and check on that. It's funny, I like took them out and all I see is like shapes. And it's like everything is really dark there in the hallways. And she
Yeah.
was like, and we'll just go to this like exam room. And I'm like, I'll just follow you.
Okay, guys. So, hi, good to see you again. Hope everybody's doing well. We were in partway through the ionization, acid-base ionization lab. And what we were talking about at that point, oh, sorry. We were back here talking about the relationship between Ka and Kb. So we knew that if we knew what Ka was, we could find Kb. And if we knew what Kb was, we could find Ka. So we went through two of these, and I left the other two for you to solve. I'm going to go ahead and post those answers. And I do still owe you results from this one. Or is it? No. this one. I haven't posted that yet, so I need to make sure that I post that as well. So I will do that. Now, what you've probably noticed as we go through this is that I go through one example with you guys, and then I go through the second example with you guys, and then I have one that I want you guys to do. And then I have a secondary set of questions that I typically ask after that that we can or can't do depending on how you feel about it. So I have a bunch more questions about using KA to find KB, KB to find KA. Given where we are, I feel like that's fairly simple. So I was hoping that I could post those answers and you guys would be okay with that. If you're not, tell me and we'll do these. Okay, so I will make sure I get those up right after class. As we continue to go through this lecture, we will have similar things for the new stuff that we're talking about. So again, I will get to a point where I will walk you through, I will give you time to do one. And then if there's more that you guys want to do together, we will do that. Oh, sorry, I went too far. Hey, where to go? Where am I? Okay. So when we talk about diprotic and polyprotic acids, this is a term that should be familiar to you. So from Chem 110, we talked about polyprotic, meaning there is more than one acidic proton. So anything that has more than one proton that can be used as an acid qualifies as a polyprotic acid. If it has two only, then we can call it a diprotic acid. And if it's three, then it's triprotic, but all of those fall into the polyprotic. So not all stuff that we see has more than one acidic proton. Something like CH3 COOH only has one proton that can act as an acid. It's the one at the end. So not all protons that we see can be acidic protons. But if there is more than one proton on it, there is a chance that those can both be acids that can be used. So H2CO3 has two acidic protons. It breaks down from H2CO3 to give up H plus and HCO3 minus. Okay, so that's the anion that's left over. But that anion can also lose a proton, become H plus and CO3 2 minus. So that is a polyprotic system. Both of those donations are separate. Each one has its own K value. Okay, no matter what, it doesn't matter what one of these we're talking about, the first K value is always bigger than the second. It's always easier to lose the first proton than it is to lose the second. So we always have K1 being bigger than K2. That's just the way it works. When we talk about H3PO4, that is the only polyprotic acid that we talk about. And that is a three-step process. So again, we take H3PO4, take off one of its acidic protons, and that leaves us with H2PO4 minus. That H2PO4 minus can not only act as a base and pick up the proton again to become this, although it really doesn't, but it can also act as an acid. And so H2PO4 minus can break down, give us an H plus and an HPO4 2 minus. Now that HPO4 2 minus is a weak acid, so it can pick up a proton when it's acting as a base. So it can act as a base, pick up a proton here and go back to H2PO4 minus, or it could further break down and become HPO4 2 minus, giving me that H plus and the PO4 3 minus. Okay, so once we've taken one of those protons off, it can act in both directions. Whether or not it does so depends on the value of the K. And again, each one of these has a K value that is associated with it. Now, having said that each K is smaller, one of the things that you might get asked about is what is the K for something like H2CO3 becoming CO3 2 minus plus 2H plus. And actually, you know how to do that because all you have to do is take the K1 and the K2 and multiply them together. So if you know both of those values and you want this one, then you can get it by multiplying these two values together. The same is true for this right here. So if you wanted it for H3PO4, coming apart to give me 3H plus PO4 3 minus, I would multiply all three of those K. Okay, so this comes directly from the work that we've been doing where we talked about if this is the first step and this is the second step, we can multiply those two Ks together to give me the overall reaction. Okay, so all of the things that we've talked about previously still apply here. So are there any questions about that?
So can you go in reverse if you given the overall K, can you like find individual ones by simply like dividing them or no?
No, because they're not the same. So you won't be able to do that.
Okay. So just one way process.
Correct. Correct. I mean, if you knew what, so in this case, if you knew what the overall K was and you knew what one of these two values was,
Right.
then you could find it. Yes, you could do that.
And like,
Okay.
does it matter? It doesn't matter the order, I guess. I guess it doesn't, right? Like you just multiply it by each other, but okay.
No, because order of operations states that it won't matter which order you do it in.
Oh.
Okay. So that's general introduction to how that portion of it works. Now, there's another reason that we need to talk about polyprotic acids. Polyprotic acids have more than one acidic proton. When we have these values, you may find them in tables that look like this, where you're given the Ka1 for that first one, Ka2 for the second one. For this one, we have citric acid. It has 3 protons that it can donate. So you have K1, K2, and K3. So again, we can multiply those values together to get an overall for that if we need to. Okay, so that is something that you can work with if that is something that you are given. So you need to understand that that is possible. So that's what we were talking about there. Generally speaking, the pH depends only on the first association. If the factor between the two K values is greater than 10 to the minus 3. Okay, so because this is 10 to the minus 5th, and this one is 10. Where did my, oh, hold on, sorry. And this is 10 to the minus 12. This one is so much smaller than the 10 to the minus 5th that it only depends on that first value. Hold on, let me get my screen share. Sorry. Okay. So again, it only depends on that first one because they're so different, right? That is not necessarily the case when we're talking about an acid like citric acid, because this value, 10 to the minus 4th, is not that different from this value right here, 10 to the minus 5th, and is not that different from this value right here, 10 to the minus 7th. So because all of those are very close together, we cannot say that we're only looking at a pH that's dependent on the first K because of that. Notice that sulfuric acid, the H2SO4, the first K is large, and therefore that is the one that determines what our pH will be. So that is the one that we typically have to look at. Okay. Now, again, I'm not going to ask you to do math with that because it's a lot of work. So I'm not going to make you do that. So questions about that part? We will come back to looking at polyprotic acids a little bit later, which is why I wanted to mention them here, because it's important that we talk about them before we get to titrations. So now, one of the things that we have not done yet is to look at how we use a pH to calculate Ka. So we've gone the other direction. We've gone from Ka and we've calculated the pH of those solutions given an initial concentration. All right. We need also to be able to use this information to calculate a Ka. And that's a slightly different use of our rice table. So we're going to look at how we can use that. The pH of a 0.1 molar solution of formic acid, HCOOH, at 25 degrees is 2.38. Calculate Ka for formic acid at this temperature. So formic acid is a weak acid. I know that that is true because it's not in my strong acid list. So if this is my formic acid, this is my H plus, this is my HCOO minus. My initial condition for my HCOOH is given to me as 0.10, and that is molar. Okay. I assume that these are 0, where I start. And I know that for every time I break one of these down, I end up with an X here and an X here. Now, everything looks fairly normal when I get to the 0.10 minus X, and we ignore the X because it's small. But now I have a value that actually can go in this H plus column, right? Because if I know what the pH is, then I know that the H plus concentration is equal to 10 to the negative pH. And so that value can go right there. And then this is X. Now, because of the way this table is structured, that means that this value right here is X. Okay, because of the way that that works. And so once I've calculated what that number is, and if I use my calculator, I can do that. So I can go second 10x negative 2.38. This is the concentration that I have for H plus. And of course, since I have 3 sig figs there, it should technically be 4 sig figs. So I'm going to write this as 4.167 times 10 to the minus 3. So that's the value that I have for that number. And that's my X. And so if my Ka is equal to the H plus times the HCOO minus over the HA, I know that this X squared on the top is 10 to the negative 2.38 squared over 0.10 minus 10 to the negative 2.38. Okay, so I can do, sorry. So I can do that math to get that calculation for what my K is. Okay. Okay. So if I take that value that I have here, I can square that. And then I can divide that by 0.10 minus that number. And that gives me the value for Ka. So my Ka is equal to 1.813 4 sig figs times 10 to the minus 4. Does that make sense? So
It
what I'm
does make
learning,
sense. For sure. Can you just like, because like the X is always the negative log of whatever, I mean, the pH is always the negative log of whatever the X number is, right? Like based on the formula.
yes,
So that makes sense. Yeah, for sure. It's like 10 to the negative pH.
correct. So this is starting to learn to use our rice tables in a different way. And this is important because you can use it in any way you need to. These rice tables are incredibly powerful and they're boring as hell, but they always function in the exact same way. And so if we get used to, what do I know? Where does it fit in this table that I have? Then I can get to some very powerful calculations by using that. Okay. So using the pH to calculate Ka is always going to be like this. Now, any questions before I slide to the next slide? Okay. So your method to follow for calculating pH using Ka is to write your chemical equation. Always write your chemical equation. Write the equilibrium constant expression, your K. Set up your table for the rice table, the ice, and plug in that concentration for using the pH. Okay. And then substitute your equilibrium concentrations into the equilibrium constant expression to solve for X if you need to do so. Okay. Now, in this case, we didn't have to do that, right? But technically, we did sort of, because you have to get that initial concentration once you've taken out what has changed. So we had to do the subtraction from the initial concentration. Okay. So cool with that. So let's try it one more time. We want to calculate the pH of a 0.3 molar acetic acid solution, HC2H3O2, at 25 degrees C. Okay. So now we're looking at this from the back side of this. So not exactly what we did previously. I changed stuff up on you. So you should know how to do this. So let's see if you can set this up. Okay. So I gave you what is the pH of a 0.3 molar solution of acetic acid at 25 degrees C. And I hope that you were able to set up your Ka expression where you have H plus times C2H3O2 minus over the HC2H3O2. And that's going to be equal to X squared over 0.3, right? Because we're going to ignore the X because it's small comparative to what we're talking about. And so we would set this up as the 0.3, the initial concentration for our acetic acid, 0 and 0 for the H plus and the C2H3O2 minus. We have a minus X on our acid and plus X for our H plus and our C2H3O2 minus. And notice I've started leaving the plus off. It's only necessary to put it on when it's negative. but it's not necessary to include it unless you need to show explicitly that it's a negative value. Okay. And so that gives me this, which I can then plug in to get this value right here. And then people go, oh, wait, I need something else. And yes, you do. At this point, we can't do anything. So we can't solve for Ka without a pH, and I can't solve for pH without a Ka. So if I got this on a test, what would I do? Well, I'll tell you what I would do. I would look at my exam handouts. And if I do that, and that's not what I wanted, don't do that. Pull this up here so that we can actually look at it. That would be helpful. I know that there's a value for Ka for acetic acid, and it's 1.75 times 10 to the minus fifth. So if I were on a test and it asked me to solve for the pH for this, I can do that. I just need to make sure that I'm looking at the resources I have available. So I need that Ka value, which is again 1.75 times 10 to the minus fifth. And therefore I could solve this for the pH. Cool. So I can plug that in, and I can put 1.75 times 10 to the minus fifth is equal to the x squared over the 0.30. I can then have that x squared is equal to the multiplication of those two values. And so if I find my calculator, 1.75 second e negative 5 times 0.3, and that gives me 5.25 times 10 to the minus 6. I take the square root of both sides. And that gives me that x equals 0.00229. And so if I needed to find my initial conditions, I could do that. If they asked me for pH, I take the negative log of that value right there. And that gives me 2.64. Cool with that. So that's one thing. And of course, hopefully that's the easier of those two. All right. Here, the pH of a 0.1 molar solution of ammonia, NH3, at 25 degrees is 11.13. Calculate Kb for ammonia at this temperature. Okay. So let's think about this for a minute. I know that the reaction between NH3 and H2O gives me NH4 plus and OH minus, right? So that's what I have there. I want to solve for Kb. Now I know that this is a liquid, so I can ignore that. I know that my initial condition for this is 0.10, and then I have a pH equal to 11.13. All right. So I'm going to stop and think for a second, because this is the way my brain works. I want to write what that Kb looks like before I do anything else. And I know that that's an NH4 plus times an OH minus over the NH3, right? Now, I know that I have a pH, which means that I can solve for the POH. So POH is equal to the pH, 14 minus the pH, sorry. And so we got 14 minus 11.13. And no, I am not going to do that because I know I'll screw it up. And that's 2.87. And so the OH minus concentration at equilibrium is 10 to the negative 2.87. Now I can solve for that value if I choose to. If I write it in like that, that works fine. It doesn't matter to me which way you handle it. Okay? Either one is okay. I know that initially I started with 0 of this and 0 of this. Every time this reacts, I get one less of those, one of these, and one of these. And so my x is equal to that 10 to the negative 2.87. And at equilibrium, that's 8.10 minus x, and the x is small, so that comes out. That means my KB should be equal to x squared over the 0.10, right? In this approximation. And my x squared is 10 to the negative 2.87. And I have to square that value divided by 0.10. Okay. So what I can do is I can take that value that I have and I can do the 10 to the negative there. And I can either enter that and then square it and then divide that by 0.10, or I can do that all as one step. It's entirely up to you how you enter that. Okay. But you should end up with KB being somewhere near 1.8 times 10 minus 5, because that's the actual value for that. And I remember that. So, and it is on the tables. So you have, I mean, your value may come out slightly differently than that. It depends on what our actual situation is, whether it comes out to be exactly 1.8. Okay. But it should be somewhere close to that. And it is here. So given that my pH is three significant digits, my answer should be 1.8 times 8. 19, that's going to round up. So 20 times 10 to the minus 5th. Is that right? That's 3. So that should be 2. So that should be 1.82 times 10 to the minus 5th. Sorry, struggling with my sig figs. So that's what I would report as my KB. Now, from a technical standpoint, should I make the correction to do the 0.10 minus that value? From a technical standpoint, yes. Okay, so we would have a more accurate value if we did the 0.10 minus this. And so if we took this number right here, squared that, and then divided it by this. That did not look right. Sorry. It's because I did my calculation on my calculator's wrong. So I need to take that. I need to square that. And then divide it by this. So that's a more technically accurate value. But you can see that it's not significantly different. Now, does that make sense? Would I accept both on a test? Technically, yes, I would.
Hold on, where is the calculation, like the 0.10 minus 0.0013? Where did that come from? I think I missed that part.
Because from a technical standpoint, this calculation or this actual value at equilibrium, when we plug it in to solve for KB, should have that correction. So I know at equilibrium, we ignore this when we solve for the x value. When we solve for x, we ignore it. But when we solve for KB, we should actually do the correction to plug that in. So this should actually be this when we do solve for KB.
Okay, thank you.
But again, I'm not going to take points out if you really don't. So cool with that. So again, it is an approximation to leave it off. And when we're solving for X, we always make that approximation. But when we solve for KB, we should be using the actual value. So do you want to do another one? Okay, then I can post those. So questions on what we've done in terms of getting to pH, getting to Ka, getting to Kb, those kinds of things. All right. Well, then we will shift gears a little bit, and we're going to start talking about buffers. Now, buffers are incredibly important. Buffers are probably half the reason that you guys have been asked to take this class. So it is important that we discuss them in some detail. So what is a buffer? A solution of a weak conjugate acid-base pair that resists drastic changes in pH is called a buffer. So there has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. These solutions contain relatively high concentrations of both the acid and the base, so times 10 to the minus 3 or more. Their concentrations should be approximately equal if it's going to work well, because if you don't have a good ratio between the acid and its conjugate base or the base and its conjugate acid, it does not buffer well. Okay. So these are resistant to pH changes. This is important. Your body is full of these things. We use these in industrial processes to make sure that we're not getting stuff screwed up when we're working with particular solutions, because the pHs are very important in determining the chemistries that we see. So it's very, very important that we are, one, able to set up a buffer, two, understand what it does, and three, do calculations about what its capacity is, how capable it is of resisting change to pH. Okay, so that's our definition for a buffer. Now, how does a buffer work? Well, initially, we're here in the middle, and I'm in an initial situation where I have the equal amounts of HF and F minus. Okay, so I could make something like that by adding HF, the acid, to NaF, which is the salt of the fluoride ion. So NaF would be an excellent way to do this. We often use Na salts because they're always soluble. So KF, NaF, those kinds of things because of their solubility. Okay, so if I have equal concentrations of both of those things, if I add OH to this solution, what happens is that it reacts with the HF, and it gives me less HF and more F minus. That happens. So because there was HF available, that takes up the OH minus. That means that the pH doesn't change because of that. Okay, so as long as we have sufficient HF available, the pH won't change. Okay. If we go the opposite direction and I add H plus to this solution, then it reacts with the F minus that's here, and that can then give me more HF. Come on, more HF, and F minus has gone down. Okay. So it reacts either direction, and it takes whatever piece went in it that should have changed the pH and makes it something that doesn't really change the pH. Okay? So that's the way that this works, is we have the ability to act with either an acid that's been added or a base that's been added to effectively not change that pH. Now there are several ways that we can make a buffer. Right? one of which is to mix a weak acid and its salt, or conjugate base and its salt together. So that's the situation that we were talking about here when we mixed HF with NaF. That's one way, okay? Because then I've added both components, and so I've got a situation where I can buffer. The other thing that I can do is take like a weak base and titrate it with a strong acid. Because if I do that, as I do that titration, the weak base becomes its conjugate acid as we do the titration. And therefore I end up with a situation where I have the conjugate acid and the weak base, or the weak base and its conjugate acid. And so since I have both of those present, that is still a buffer situation. So as we start talking about titrations, we'll find that every titration that we do, as long as there is a weak component in it, will end up in a buffer situation. Okay, so that's an important part of this. And those are the two ways that we typically look at making these solutions, either by mixing them directly or by doing a partial titration. Okay, so as long as we don't add as much base as we had weak acid, or as much acid as we had weak base, then we're in a buffering situation. Okay. So those are the ways that we can make these things and how they act. Questions about that part? Now, the range of pH values over which a buffer system works is in their optimal pH, where pH is equal to the pKa plus the log of the base times the acid. If one concentration is more than 10 times the other, it doesn't work very well, okay? And because of the math that goes with that, that means that we're typically looking at a range of plus or minus 1 pH unit from the pKa of the weak acid or the pKb of the weak base. Right? So plus or minus 1 pH unit is typically what we're looking at. All right. Now, the amount of acid or base the buffer can neutralize before its pH begins to change is dependent on what that concentration is. So the more I have, the more there's present, then the more acid or base I can take in before the pH changes. If I have a very small concentration, like 10 to the minus 3, then I don't have a huge ability to do this. All right. And we use something called the Henderson-Hasselbalch equation to do these calculations. Now, the pH will be the same for its conjugate acid-base pair if it's a 1 molar or 0.1 molar, but the buffer range over which it can work will be different. So the ability to buffer is based on how much there is. The pH is based on what the identity is. Okay. So let's talk about the Henderson-Hasselbalch equation. Now, we'll write that equation in just a second, but I want to talk just for a slight bit more about how this works when we add stuff to it. So again, if I have my buffer, it contains both HA and A minus in this case, so weak acid and its conjugate base, and I add strong acid to it, then I'm going to react with the A minus. That'll give me back HA. I will then need to calculate the new values of HA and A minus, and then use that to be able to calculate the pH. Okay. When we add a strong base, that strong base will react with the HA component. So the HA and the OH minus down here will end up with A minus and H2O plus. We'll need to calculate the new values of HA and A minus after that reaction happens, and then use that to calculate the new pH. Okay, so this is always a process of, we have to look at, I added this thing, I have to calculate a new concentration, then I can use the Henderson-Hasselbalch equation to figure out what that pH will be once I've done that. Okay. Now, for a weak acid, I know that Ka equals H plus times A minus over HA. If I take the negative log of both sides, so I take the negative log of Ka, that's equal to the negative log of the H plus the negative log of A minus over HA. So all I've done is separate these two, pulled the H out, and left the other two together. And I did that because if I take the negative log of the H plus, then I know what that is. And if I take the negative log of the Ka, I know what that is. Now, if I rearrange this whole thing so that I leave the negative log of H plus over here, right? Where's my pen? Over here, and I move this to the other side, right? Then I add this to both sides, and so I end up with the negative log of H plus is equal to the negative log of Ka plus the log of the A minus over the HA. Okay, so I've rearranged that equation. And I know that the negative log of H plus is pH, the negative log of Ka is pKa, and then I add the log of the A minus over the HA. That equation is known as the Henderson-Hasselbalch equation. Okay, this applies only to situations that are buffers. Okay, so I have to have A minus and HA present for this to work. Right? So I can't be in a situation where I've only got one of those things and this will work. This is the Henderson-Hasselbalch equation. I will guarantee you that I will at some point today refer to this as the Hasselhoff equation, because in my head, that's how it exists. And I'm sorry that that's true. But the only way I could remember the name of the equation was to refer to it as David Hasselhoff, so that's what you get, and I'm sorry that it stuck in my head that way. So, Henderson-Hasselbalch, pH is equal to pKa plus the log of the base over the acid. Okay, now while there is a version of this for pKb, there is, we typically don't use it. We typically will refer to this in terms of the acid components and not the base components. We can do this without using the Kb ever. So you can do this in terms of only the acid. So it is, a lot of chemists don't bother to remember the other equation. So this is what you'll typically see. All right. So this would be how we would calculate the pH once we've made those changes, is to look at how much A minus and how much HA is left, and therefore we can calculate what that pH is. Okay? So I've told you a lot of stuff about what it is and how it works. Let's see if we can talk about what it actually looks like. So one of the things that you might see, what is the pH, the pOH, the H plus, and the OH minus for a buffer that is 0.12 molar in lactic acid, CH3CHOH, COOH, and 0.1 molar in sodium lactate. The Ka for lactic acid is 1.4 times 10 to the minus fourth. Finally, what is the concentration of CH3CHOH, COOH in solution? Okay, so this is what we're looking at. Now, I know that I can use the Henderson-Hasselbalch equation to do this. And that's the steps that you're looking at here. But what I would do is I would set this up. pH is equal to pKa plus the log of the base, which is the lactic acid, or the sodium lactate, so that this portion of it. So the base portion would be everything minus this H. So CH3CHOH, COO minus, and I'll get rid of that. Sorry. Over that acid, which is the concentration of CH3, CHOH, COOH. Okay. So that's what I'm looking for in terms of plugging things in. So when I do that, if I want to find pH, I know what the Ka is. So I take the negative log of that Ka, which is 1.4 times 10 to the minus fourth. Then I have plus the log of that base concentration, and it told me that my sodium lactate is 0.10. And my acid concentration is 0.12 molar. And I can do that math. So I take the negative log. Where's my log key? 1.4 second EE negative 4 plus the log of the concentration of that base, so 0.10, divided by the 0.12, that acid. And that gives me 3.77. So because I was looking at a situation where I have 2 sig figs for both of those, I report this as 3.8 for my pH. Now, and you can barely see that. I'm sorry. So cool with that. So that's my pH. If I wanted to find all of the rest of it, my H plus is 10 to the negative 3.77, which is this number right here. My POH, 14 minus the 3.77, because I listed that whole thing there, which gives me 10.23. My OH minus is 10 to the negative POH, which then gives me 5.98 times 10 to the minus 11. And of course, if I were to do the actual concentration of the CH3CHOH, it's that initial value minus this value that's gone to H plus, which gives me this right here. Okay, so we have to do the correction for that. Now, does that make sense?
I feel like I'm a little lost with this one. I keep getting the wrong. I don't have the same calculations up at the top for the pH. Like I keep getting 3 point. It's just not the same. It's like close, but it's not the same.
So I ended up with 3.77. Did you close your parentheses on the first log term?
Yes.
And when you did this, the log term over here, was it 0.10 divided by 0.12?
For which one?
Or,
Oh,
so
yeah.
your log
0.10
okay.
divided by 0.1. Oh, I think I did 0.20. Okay, thank you. I'm sorry.
No, that's totally fine. Trust me, it often takes a second pair of eyes, which is why we always do that in the lab, is to make sure that we've got everything exactly what it's supposed to be. Totally fine. So cool with that. And again, the note at the bottom states that all of our sodium lactate, since it's an ionic compound, will dissociate. So your concentration there is 0.10. We always put in the 0.12 for the bottom term because that's what we have to start with. So that's what we always do. But when we're looking at what is our actual situation for our equilibrium, we know that some of that has dissociated, and that's why we do this calculation right here, is to take into that dissociation and take that into account. Okay? So again, do you need to do this way? No, I have students who do not approach it this way. I have students who approach it through a rice table and do it the exact same way with the Ka. You should get the same value. This is no different than what we've done before. We've just taken the negative log of the whole expression. So it just looks different, but it's not different math. So if you wanted to work it that way and you're more comfortable doing that, that's totally fine. But you will need to learn to use the Henderson-Hasselbalch equation. So at some point you need to do that. Okay? So Shall we take another look at this, or are you guys comfortable? And either way is fine.
Yeah, can we do one more, please? That's possible. Thanks.
Yes. So we've got this 0.234 molar oxalic acid, so C2H2O4, and 0.230 molar sodium oxalate, which is Na2C2H. HO4, that's correct. Sorry, we took a proton off. That's correct. And it's mixed together. That's not mixed together. The Ka for this acid is 0.056. What is the pH of the buffer? Also, what are the pH, POH, H plus, and OH minus? And how much C2H2O2 are left in solution? So, the equation on the exam handouts, the Henderson-Hasselbalch equation, is there. And it says pH equals pKa plus the log of the base over the acid. So, pH is equal to the pKa, which is the negative log of the Ka that they gave me, and the Ka is listed here as 0.56, plus the log of the concentration of the base, which is right here, the sodium oxalate, 0.23, I can write that. Sorry, wrote the wrong thing, 2.30. And then my oxalic acid is 0.234. Okay. So I can do all of that lovely stuff right there to solve for my pH. And so again, I have a negative log 0.056. I add to that the log of the base concentration, the 0.230, divided by the acid concentration is 0.234. I have an extra parenthesis, so I'll go ahead and close that. Oops. So, and that gives me 1.24. Now, again, I don't grade you guys for sig figs on this, so I'm not going to worry about it too much. So that's my pH at this point. All right. If I have a pH, I could find the H plus, and that would be equal to 10 to the negative 1.24. My OH minus, I'm going to leave for just a second. My POH is equal to 14 minus 1.24. .76. And so my OH minus is 10 to the negative 12.76. And I think the other one they asked me for was the C2H2O6, which is equal to the 0.234, the initial concentration, minus the H plus, which is 10 to the negative 1.24. So doing that correction based on the dissociation. So 0.234 minus second 10x negative 1.24. And 0.176. And that happens to be molar. And again, I'm not going to worry too much about the units on that. We as chemists typically leave them off, so I'm not going to worry too much about it. Okay, but that's how I would calculate all of those values. So it's the same kind of thing that we've gone through for everything else. Now, do I actually want you to calculate what these values are on a test? I'd like to see you do it once. I will be perfectly honest. I want to be sure that you know how to use your calculator to get between these expressions that we've written and the actual numbers. But you only need to do it once. The rest of the time, if you just want to leave it like this, that's perfectly fine because it's going to save you a lot of time if you do. So I would prefer that you do this at least once where you show the actual values, and where you do that is entirely up to you. I will probably specify on one of them that I want the actual numbers, because then we're all doing it in the same place and I don't have to look over the whole test to find it. But it does save you a lot of time if you don't bother to do the calculation. So does that make sense? Now, if you want to, you are perfectly welcome to. I would not have left this on my paper as a student because it would have freaked me out. It's just something I was trained to do. But it's totally fine if you guys want to leave it, because we all know what that means. So, okay.
Okay, can I just leave it as a pH as a negative log of 0.056 plus the log of 0.23 over 2.34? Was that the acceptable answer?
Well, no, because you didn't actually solve for a value for pH. Because I specifically asked what the pH is, what that value is, I need to know what the number is. So I didn't ask for an expression, I asked for a value. So on that one, I need to see what that actual number is.
How did we
Again,
how do we know what math to do to get the concentration of C2H2O4 left in the solution? So is it like it's go ahead, sorry.
Go ahead. No, go ahead.
I was just gonna say, so I see it's obviously like the oxalic acid minus the H plus concentration. But
That's
why
correct.
is it?
Because
why do we need that?
Because you know you've dissociated some of that acid, that's why your pH is what it is. So you have to do the correction to the concentration of the acid to show that some of it has dissociated. That's why. So your concentration for your acid is always the initial concentration minus the pH, because that's what has dissociated. Well, the H plus portion of pH. So, because that's what's dissociated. That's why your pH is what it is.
Okay, thank you.
Mm-hmm. So yeah, typically on the, go ahead.
Is it based like on the fact that it is an acid and you technically dissociate the H plus? So that's why you do initial concentration minus the H plus. But if it was like a base, would you do the same thing? It would be like the initial concentration minus the OH concentration?
Correct.
Okay.
Correct. And
Because
I'll give you a hint. It's usually whichever thing I ask you for that's not pH, POH, OH minus, or H plus is usually going to be the one that you'll subtract either the value of the H plus or the OH minus from, because that's the only reason I ask about it.
hold on, say it again.
So notice I didn't ask what the concentration of the N2C2H04 is, right? I only asked what the concentration of the C2H2O4 was. And the only reason I ask for that is because it's not what it says it is in the beginning. So I need to know that you know how to do the correction. So anything that I'm asking for that is not pH, POH, OH minus, or H plus is typically the one that has dissociated. So it either acted as an acid and dissociated to give you the H plus, or it acted as a base and picked up a proton from water to therefore become the conjugate base.
I'm so confused. I'm sorry.
No, so I always ask for the same couple of things, right? pH, POH, OH minus, and H plus, right? They're always there.
Right. Mm-hmm.
But the only thing I ever ask about beyond that is whatever has done the dissociation. So in both of these cases, they've been acids. And so we've dissociated that acid to give us H plus, which therefore generated the pH, right? So it's always been the acid concentration that I've asked about, the C2H4O2 here and the lactic acid on the previous slide. If I'm asking about something, it's because it's the one that that reacted with water to generate either H plus or the conjugate base. So I'm
Okay.
looking for that correction.
But doesn't it dissociate completely, or is that the question is how much of it left in the solution because it didn't dissociate?
What no? Okay, wait. This is a weak acid, right?
True, so it doesn't dissociate completely. That's why.
Correct. Yes, that is why. You can never do this with a strong acid. It
Okay,
won't make a bubble.
and because you know it's an acid and it gives away H plus, you subtract.
Correct. Or it's a base, in which case it's become the conjugate acid. So those are the ones that I would ask about. And I almost always ask about the acids. Don't worry too much about the bases. I mean, you'll have to get tortured with that on Alex. I won't lie. But, I'm not going to do it to you on a test. So.
Okay.
Okay. So use the questions that I've asked and the way that I've asked them as a hint, because again, I only want to know because that's the thing that's dissociated, and that pH tells you how much has dissociated. So we can then use that to do some other things. We're going to talk about percent ionization for these acids. And so we need to know how much actually dissociated to be able to calculate that. So that's a step towards calculating that. We'll get to that in a little bit. Okay. All right. So, do we want to see another one, or do you want to have you guys work on this and I will post an answer to it so you can see how you did?
Can we do one more if that's possible?
Yeah, we've got one more.
Mm.
So we've got a 0.0137 molar benzoic acid, which is HC7H5O2. It's mixed with 0.020 molar sodium benzoate, which is NaC2H5O2. Okay. What is the resulting pH, pOH, H plus, OH minus? And here I asked for both the benzoic acid and the sodium benzoate of the solution. Okay. So I'm looking at this, and I know that I'm looking at Henderson-Hasselbalch. It's a buffer. I have a weak acid and its conjugate base, so it's definitely a buffer situation. And so I'm going to be looking for this equation, and my A minus, the base portion, is the NaC2 C2H5O2, and I know that because it says sodium on it. So that's my base. My acid is the HC7H5O2. Wait a minute. That should be a 2, not a 7. No. Wait a minute. They should all be 7s. I copied the wrong thing. Okay. Sorry about that. So the subscripts on this, that should be a 7. That should be a 7. I apologize. That was my bad. So this is my base. This is my acid. So if that is the case, then that should be the form of the equation that I need to work with to make
So we
this work.
always do the base over the concentration of the base over the concentration of the acid?
Yes, it's always A minus over A. HA, yes. Yeah, as long as we're dealing with pH equals pKa, that is correct. So if I have that, I need to find the Ka for my benzoic acid because they didn't give it to me. So I need to go find it. And that would be on my exam handouts. So I should be able to find benzoic acid, which is right here. C6H5COOH. And the value that is given there, I can't get to my
6.25 times 10 to the negative 1.
I can't tell what the 10 to the negative. Oh, it does say 10 to the negative 5. Okay, thank you. Times 10 to the negative 5th. And so I need to take the negative log of that. And then I need to add the log of the concentration of my base, which is the 0.0200 over the acid, which is 0.0137. So calculator has disappeared because I covered it up. So negative log 6.25 second EE negative 5 plus the log of the 0.0200 divided by 0.0137. And that gives me 4.36. Technically, do it that way. Okay, so that's my pH. So that's the pH. My pOH is going to be 14 minus that value, and I'll calculate that in a minute. My H plus will equal 10 to the negative 4.36. My OH minus will be 10 to the negative whatever my pOH is. So and if I wanted to calculate all of those, I would do that. I'm not actually going to, but the other two concentrations that they asked me for, I got asked, wait a minute. Thank you. C7, H5, O2, and my A C7, H5, O2. Now, really, part of this is supposed to be a gimme. So this concentration right here, the concentration of my base, is always going to be exactly what it was, as long as I haven't reacted this with something else. Okay, so this will be 0.0200 molar, because I haven't reacted it with anything else. So I haven't made any more of that, and I haven't used any of it up. So that's the concentration that it will be, because it completely dissociates. All right, so that's the base situation, and that's always how the base will work. With my acid, I always have to take that 0.0137 that I started with and subtract the concentration of the H plus. And that will be the response that I need to list for that. Okay, I did it wrong. I love it when I do that. I forgot this. I forgot the negative. So that's 0.013. And that technically still rounds up to 137 if you're reporting 3 sig figs, because the amount of the dissociation is very small. Okay? So cool with that.
I got it.
Okay. So any questions?
Nope. Is there a question that's like, is it always going to be an acid and a buffer, or is it going to be a base and a buffer?
Alex will ask you about the base portion, and let me pull up. Give me 2 seconds. Let me pull up the exam handouts. Let me find my useful equations. So this version right here is the version of the Henderson-Hasselbalch equation that's on here. Given that that's the only version that they've given you, that is the only one that I expect you to work with on the test. So there is a version for bases, and I think it's in the lecture. I'm not sure. I'm not even sure that I provided it, but we'll get to that. If I didn't, I can definitely look it up for you guys because I don't remember it. So, but that's the one I will expect you to work with on the test. So, on Alex, they will probably ask you to work with some that are bases as well, because we don't exist completely in a space where we work only with the acid components. Now, like I said, for me as a chemist, if I'm working with a base, I typically will find its Ka and therefore do the equations using the Henderson-Hasselbalch in the acid form rather than working with the base directly. But that's just because I'm lazy. So I don't want to have to remember the other equation. Okay. Now, we've talked about very simple, hey, I'm going to calculate based on these concentrations. And that's the easy part. The not so easy part comes when we start looking at what does a buffer do when it's in action. So if I tell you that I have a buffer that's made by adding 0.3 moles of HC2H3O2 and 0.3 moles of NaC2H3O2 to enough water to make 1 liter of solution, then I tell you, calculate the pH after 0.020 moles of NaOH is added. So 5 milliliters of 4 molar NaOH was added. And we want to know, what's the pH now? I clearly had a buffer to begin with. And I know that because I had components from acetic acid, which is HC2H3O2, and I had sodium acetate, which is NaC2H3O2. So I clearly had a buffer before this started, right? So in my initial conditions, before the reaction starts, I have 0.300 moles here. I'm ignoring this, and this is 0.300, and that's too many zeros, moles here, because that's what they told me. So I have 0.3 moles here, 0.3 moles here, and I've diluted that to 1 liter. Now I want to calculate the pH after I add 0.02 moles of NaOH. Let me ask you, what happens in my beaker when I add that NaOH? So I add NaOH, I take NaOH, and I add it to this system. And this system contains this acid, CH3COOH, which is just another way to write that same acid. And I also have this, the CH3COO minus. Now I know in my head that the NaOH is not going to react with this component right here, because this is a conjugate base. The base will not act with the base. So I know the reaction that I have to be worried about is this one right here, okay? And I know that I have 3 moles here, and I have 0.020 0.020 moles here. Now, I can tell from looking at those that I'm going to react all of this base with some of this acid, and I'm going to have some of this acid left and none of that OH. So what happens when I do that is I end up with an NaCH3COO plus H2O. And so the amount that gets converted from here to here, which should be 0.020 moles, is going to add to this and subtract from there. When I do that conversion, it's a 1-to-1. So every time I react one of these, I get rid of one of these and make another one of these. So this is what happens mathematically when I do that, as long as I'm considering this in moles. We cannot consider this in terms of molarity because molarity is moles per liter. So it has to be done on a mole-to-mole basis, right? And this changes if the stoichiometry of the reaction changes. So if I were to react this with something that was diprotic, then that would be different than what we're talking about here. But because we're talking about a situation like this, that typically is not the case. Okay, so it's typically going to be a 1-to-1 relationship that we're looking at when we talk about the buffers. Okay, so the change that we see here is the 0.020 moles. And I'll move that out of here because I put it there. And this one is going to be plus 0.020 moles. It goes there. Okay. So that's what I've got there. Now, initially, when I put that 0.0, so once I mix it, this is here. But that's how we get this change that we're looking at. And so after that reaction is over, have that 0.3 minus 0.02, and that gives me 0.280 moles and 0.320. And again, that's in 1 liter. So I know this is the same as the molar in this case. That's not always the case, but it is here. Now that I've seen how much I've changed this, then I can calculate the pH again, right? Because I know that my pH is equal to the pKa plus the log of the base concentration, the 0.320 over the 0.280. Okay, because those are my new concentrations. And again, those have to be in molarity when they go into this. So if you were in 2 liters, it would be half as much. Okay, so make sure that when you do this calculation, this has to be in molarity, not moles. But this calculation has to be done in moles. All right. So I tried to make the math a little easier here by putting it in 1 liter, but it's not always the case. So looking at my acetic acid, I pull this up and find my
Okay,
table.
could you just let's say hypothetically you do like a different amount than like a liter. Like how would you put that in the equation?
So once you have your number of moles, you divide it by the volume. So if I'm looking right here, my 0.280 moles, if that was in 1.5 liters,
Then you would just divide that by
I would divide it by the 1.5. Correct. So you just need to make sure it's in moles per liter and not just moles. So whatever your volume is, I don't care what it is, you divide by that volume in liters. Does that make sense? So my lovely acetic acid that I've got here. So CH3COOH 1.75 times 10 to the minus fifth, because I know that's what that says. So I have the negative log of 1.75 times 10 to the minus fifth plus the log of the 0.320 over the 0.280. Okay. So looking at that math,
Okay.
negative
One more question. So you use
yes,
molarity in that log of the base over the acid thing, right?
correct.
So that's where you get 0.32 over 1 liter. So that's where the molarity will like come in the picture. So up until then, you just do the moles, and then if you need to figure it out and put that into this equation, it would be the log of what that would be in molarity.
Correct.
Okay, so
Correct.
now it makes
Yes.
sense.
So yeah. Yeah. And I end up with a pH equal to 4.81. Okay. So again, this is thinking about what is the chemistry that's gone on when I did that addition. So I have to think about this balanced reaction here. I did that chemistry right there. That looks at this change right here based on that. Okay, so every time I convert one of these NaOHs into this the acetate ion, then I have to add to the acetate ion and take it from the acetic acid. That gives me these new concentrations in moles, which are divided by the 1 liter for this solution, to plug into this equation to calculate the new pH. And of course, if we were to look at what it looked like before I did that, what was the pH before that? It would just be that negative log of the pKa, because those two things were equal to each other. So if I take that, I get this value, which is 4.75. If you were to take the negative log of the 1.75 second E to the negative fifth, so the pKa, plus the log of the 0.300 divided by 0.300, you would end up with the exact same thing. Because as long as you're taking the log of 1, it's 0. So that's how that works. As long as that log portion is of 1, then that is a 0 value that you're adding to your Ka. Okay? So cool with that.
I do have one more question, if that's possible.
Yes.
Okay,
Yeah.
so the 0.020 that you have in the OH concentration is because the NOH completely breaks down. So, and since it's a 0.02 molar of the NOH, you would get 0.2 molar of the Na plus and 0.2 molar of the OH minus, right?
Correct.
And
Correct.
that's why you would subtract that number on the left side, because the concentration goes down, and on the right side it's a plus sign because the concentration goes up.
Correct. Because every time I run through this equation and I take one of those OHs and I react it with the acid, then I generate another one of these CH3COO minuses. That's correct.
Okay, that's a little bit more understanding.
Okay. So you might, in theory, see a question like this where you get asked, if I do this addition, what happens to the pH? If I do this addition, what happens to the pH? Be careful when you do these kinds of questions because they're often stepwise. So you might get asked, okay, this is what happens after I do the, 5 moles of this 4 molar NaOH. Oh, go ahead. Okay, never mind. So you might get asked what happens to the pH after I add 5 mils of this 4 molar NaOH, which would be this first step that we've done right here. But then they might ask you, well, what happens if I add 5 mils of a 4 molar HCl? And so that's considering where you already are. So don't forget that you've done those one after the other. And so your situation will be different for your second addition than it is for your first. Okay?
What?
So we might ask you, what happens if I then add,
Do this number like 5 milliliter of 4.0 molarity of NOH, is it just like there just to kind of throw us off? Like, do this numbers even
no, that's
matter?
exactly how I got this number.
Oh, right,
That's how,
Okay,
that's how I
okay.
got that. Yeah. So don't forget that because you know solution stoichiometry from 110, you might get presented this rather than this, but they are exactly the same. So I might expect you to calculate the number of moles based on this right here.
I mean, moles over volume liters.
Yes, so I would convert this to liters, multiply those two together, and that's where I get this value right here. Yes.
So
So if we were to consider that, I would take the 5 milliliters that I have, divide that by 1,000 to convert it to liters, multiply it by the 4, and that gives me 0.02 moles of whatever I'm adding. Here in this case, NaOH. Here in this case, HCl. So that's where that comes from. So, and again, I put it both ways because I wanted you to understand that you might see either one of those on a test. But again, if you were to add the HCl portion afterwards, you would now be considering this as your new initial line, and then you would have a change below that and an after reaction after that. So don't forget that it's stepwise. Okay? And that's what I was talking about here is we could, after the above solution change has been made, we then add 5 milliliters of HCl. What's the new pH? So that's what I was talking about, adding that second thing to it. So, and of course, in this case, we would need to know what the molarity of that solution is, because otherwise you can't do it. Okay?
So would you use the same Ka for the
Yes.
pH3COOH?
Yes. If it's the same system, yes, Ka will not change. It only changes if you change the temperature. So, questions about any of the stuff that we talked about with buffers? So I owe you some answers. I will get those posted right after class. And we're going to see how far we get with our titration salts. And that will determine what's going to be on the test and what's not. In all likelihood, we will stop right about buffers. So, but let's see how far we get. When we talk about titrations, we have talked about titrations before. It's not like we haven't. And we did actually do a titration with a strong acid into, or actually, no, we did a strong base with a weak acid. So when you did the vinegar reaction, that was a weak acid. That's actually acetic acid that you titrated with a strong base. So it's not like you've never seen one of these titrations before in practice. But now we need to talk about some of the things that go along with that. Okay, so the math that we didn't do last time that we will need to do this time. Before we get to that, we're going to talk about one more thing that we didn't talk about last term that we really need to talk about, and that's the acid-base properties of salts. So we're going to talk about that. We'll talk a little bit about homogeneous versus heterogeneous solution equilibria, and then we'll get back into titrations and indicators. Okay. So we have three types of salts that we're going to need to be worried about. One of which is a neutral salt, one of which is an acidic salt, and one of which is a basic salt. Now, what do I mean by those terms? What I actually mean is where we got those pieces from. So when we talk about something like NaCl, NaCl is considered a neutral salt. It is the conjugate of a strong acid, HCl, and the conjugate of a strong base, or sorry, wrong direction. So HCl here, NaOH here. So conjugate of a strong acid and a strong base. And therefore we know because of the conjugates of strongs, they're not going to react with water, right? So I won't get any pH changes because of those species. So anything that's made from a strong acid, strong base, we consider a neutral salt. Okay? That's what we mean by neutral salt. When we talk about an acidic salt, we're talking about something like NaF. So, oh, actually, that's backwards. It goes over here. Brain is not working. So NaF goes over there. I'll get to that in a second. When we talk about these guys, we'd be talking about something like NH4Cl. So this is a salt derived from a strong acid. So HCl would be the acid in question, and then a weak base. So reaction between NH3 plus HCl would give us an NH4Cl. Now, because they're both ions that come together, that gives us one product. We don't end up with the water out of this. But that's the kind of thing that we're talking about. So strong acid, weak base gives us this salt down here, NH4Cl. Now, this NH4Cl is problematic because when it comes apart, I get an NH4 plus and a Cl minus. So when it dissociates, that's what I get. That HCl, this Cl minus that came from the HCl won't back react to give me an HCl. I know this because that's a strong acid. But this right here is the conjugate of a weak base. It itself is an acid, not a great one, but an acid. And because it's an acid, it can do this. It can back react with water to give me H3O plus and NH3 again. Okay. The fact that it does that and acted as an acid and generated this H3O plus means that that salt in and of itself can change the pH of my solution. So that neutral compound that I put in there will therefore affect the pH. That's problematic. Okay. The same would be true if we took NaF. So NaF can be made from reacting NaOH plus HF to give me NaF and H2O. But this NaF, again, because it dissociates, gives me an Na plus and an F minus. That Na plus, I know because it's the conjugate of the NaOH, isn't going to back react, but that F minus will. And it'll react with an H2O to give me an HF back and an OH minus. And that OH minus will change my pH. Okay. So we have to watch out for these things that have been generated from that kind of thing. And again, I could just be putting this salt in there for some purpose so that I can look at, okay, I need to add NaF because I need an F minus salt, and the Na is just, you know, a counterion, but I need that F minus salt, but I may not be thinking about the fact that that's changing my pH. Okay, so we have to start to think about that. One of the ways that we talk about this in terms of thinking about that is to look at this table that's on our exam handouts. And so what we see is that we have the properties of the salts. Okay, so if the cation came from a strong base and the anion came from a strong acid, that won't affect my pH. We talked about that. So the pH will be about 7. But if the cation came from a strong base and the anion came from a weak acid, like this, so that we have a CH3COO minus or an NO2 minus, those can react. That anion is the problem that I have, and it means that my pH goes above 7 because I generate that acid again and the pH goes up. If I have a cation from a weak base and an anion from a strong acid, so the NH4Cl, like we talked about, that cation is my problem, and that means that my pH will go below 7. Okay. And we're not going to worry about these last 2 lines. Now, the problems with these is that we haven't talked about what really happens with these charged species down here, and these are all Lewis acid, Lewis base type things. We also haven't really talked about what will happen when we have a situation where the anion and the cation can both react that way, because it's a complicated situation. And it depends on whether the Ka is bigger than the Kb, whether it'll be below 7 or above 7. And I'm not going to ask you to worry about that. We don't worry about that at this point. Okay. But we are going to ask you to be concerned about these situations right here. So you may have a situation where you generate like NaF, and we have to think about the fact that that's going to be able to potentially change our pH. Okay, so you may get asked, if I put NaF into solution, what happens to the pH? That's where you would see that. Okay, so NaF, NH4Cl, things along those lines. It may not be something that's directly on this list, but it might be. Okay, so think about that. If you're getting asked about the pH when you've put an ionic compound into that solution, you need to think about whether or not it's the conjugate of a weak acid or a weak base, because that's why it would change the pH. Okay. And that is something that we have to keep track of, because a lot of times we'll make, I mean, chemists do that all the time. We make a solution, the pH is not what we expected. Oh, wait, it's because of that. So that's something that we have to keep in mind. Okay. So that's where that types of salts comes in. So that's something that you'll need to be aware of. Okay. So you might get asked to predict what is the pH if I put one of these solutions in. So again, thinking about this, that Na is not going to be a problem for me. The F will, because the F minus reacts with H2O to give me HF and OH minus. My pH is less than 7. When I look at NH4 plus the H2O, I can get NH3 back and H3O plus. Oh, sorry, wrong direction. I went the wrong direction. That makes my pH go up, not down. This pH is less than 7. I apologize. But that's the kind of thing that you'd be asked to look at. Okay? Does that make sense? This one would have no effect because RB doesn't react with water, BR does not react with water. So it's not listed over here as anything I need to worry about. So RBBR is actually right there. It does not affect my pH. With this one, I have COO. Which is actually a minus, that can react with H2O to give me an H2COO. And OH minus, and that means my pH is greater than 7. Okay. Cool with that. Need better distinction between my arrows and my 7. It's bad. All right. And I will post those. Give you some time to think about that. So questions about our salts, how you might see that. Now, a reminder, when we do titrations, we have something that's in our beaker and or Erlenmeyer flask at the bottom, something that's in our burette, which is our titrant. We are titrating this thing, monitoring the pH, either via indicator, via pH meter. It depends on what we're talking about. Okay. We are always looking at our equivalence point being the stoichiometric amount of acid equals the stoichiometric amount of base. So I have the same number of moles of acid and base. That's my equivalence point. If we are using an indicator, we will have a point slightly beyond that where the color changes, and that is called our end point. So that's where the color change happens. Those two things are never the same. So our endpoint is always beyond our equivalence. And so there's always a titration error because of that. We end up with a difference between the equivalence point and the detection point where we can tell that it's changed. So there's always a gap between those two things. Okay. If we're titrating a strong acid with a strong base, then we get this very nice, very clean equivalence point right here in the middle at pH 7. And we get this huge jump between the acid portion and the base portion. Okay. That means that down here, all we've got is acid. We've titrated this with a strong base. Up here, all we have left is base. So that's all determined. The pH is all determined by that base. So that's what we see. Strong acid, strong base. Doesn't matter whether we start with the acid or we start with the base, because we could do this the other direction. Doesn't matter. We end up with this very strong change right at pH 7. Okay. So that's what we get. That's great. That's awesome. We understand. In theory, we've done, like I said, same kind of thing that we see when we start with the base side and then titrate with, with the acid being added to it. So it's just flipped over. Okay, but it's the same kind of very strong equivalence point right there at pH 7. When we talk about doing a weak acid or a weak base and we're titrating with a strong, that's not quite as neat. It's not quite as pretty. All right. What we end up with is a very shortened equivalence point. It's not as tall when we're looking at it. Okay. And we can use the Ka to find the initial equivalence point. So the initial pH. We can use the pH in the buffer region. Oh, buffer region, because we've done a partial titration on a weak acid, and therefore we've generated the weak base, and therefore this region right here is called a buffer region. Okay, we can use the pH there the pH can be found using the Henderson-Hasselbalch equation because it's a buffer region. So we need to figure out how much acid is left, how much base is left, and therefore we can use the Henderson-Hasselbalch to find what the pH is in this region. Okay. This is because we have a weak acid that we're titrating with a strong base. Okay. The equivalence point is greater than 7, and it's because that salt, when we generate it, can back react with the water to raise the pH. So we just talked about that. So that pH at the equivalence point is going to be greater than 7. You can use the conjugate base of the weak acid to determine the pH at that point because we'll know how much we have. Okay. And as more base is added, the pH levels off up in here, and that's because this is generated by the strength of that base that we're at. So that pH is always determined by that. And it's exactly the same as what we see for strong acid titrations. Okay. The only thing that's going to be a little bit weird is right in here. So here we have our buffer region. Here we have our equivalence point, which is slightly above 7. We can use this point, these points in here can be determined by how much of the conjugate base we have. So all of the rules that we've been talking about so far with our KAs and our Rice tables and the use of the Henderson-Hasselbalch equation will apply to all of these points in our titration curves. Okay. So does that make sense? Now, there are a couple of other things that are different between a strong acid and strong base and a weak acid strong base, which is what we're talking about right here. So that's what we're looking at based on the pHs that I'm looking at. So if I'm looking at a situation where I have a strong acid, it starts down here, very, very, very acidic, and goes through this really incredible, point right here to get to that equivalence point right there at pH 7. Okay, so that's what we see. As that acid, so this Ka is 10 to minus 2, this is 10 to minus 4, this is 10 to minus 6, this is 10 to minus 8. So we're getting weaker as the acids go up. As that happens, we see a shortened equivalence point, a shortened jump in that middle because it's a weaker acid. Okay. We know that this is flattened out because we have more of a buffer region in here. We have more place to make that buffer region. We have more space to work in it because of that. Okay. So down here, we have much more ability to work in a buffer region because this is a strong, weak acid. Strong, weak acid. Yes. So it's a better weak acid, and therefore we have more of a buffer region. We have less as we go up. Okay. And the pH at the equivalence point is greater than 7 for anything that is not a strong acid. So you can tell from the shape of that curve whether it's a good weak acid or not such a good weak acid. And we can tell things about that acid based on where those lines appear and the definitions of those lines. So again, we can use the Henderson-Hasselbalch equation when we're doing these titrations to figure out not only what kind of buffer region we're working with, but we can also use that to determine the Ka. And we'll talk about how we do that. Okay. So that's how they're different, how they look different. Now, I told you that we need to talk about diprotics for a reason when we talked about our titrations. And that's because what we see when we do a titration with a polyprotic acid is that you end up with 2 equivalence points, one for each of those acids. So as I continue to add base to this system, I end up with 1 equivalence point here. So there's 1 sharp change in pH that goes on right here when we're talking about the H2PO4 minus. Okay, so as we've taken off that first proton, we end up with 1 peak right there. Okay, as we continue to add base, we end up with another peak from the removal of the second proton. And if we were to talk about the third one, because there is a third one that exists over in this region over here that you can't really see, that would happen because we're removing that third proton. So for each peak that you see, that indicates a different proton that you've removed. And they're very separate because each one of them has its own K. So the fact that you see more than 1 peak indicates to you that that is a polyprotic acid. So I can show you something that looks like this. And I can say to you, is this a monoprotic acid or a polyprotic acid? And you should be able to tell me that it has more than one proton. From this graph, the way that you see this graph right here, you should be able to tell me that there are 2 acidic protons because there are 2 peaks that you can see. There is no way for you to know that this is H3PO4. There's no way to know that. The only reason we know that is because that's how it's labeled. Okay? But because of this, I could tell you that that is a diprotic acid and that there are 2 protons being removed, one being removed right here and one being removed right here. So you should be able to make that kind of identification from a titration curve on a test. Okay? If you only see one equivalence point, then that's a monoprotic acid. Okay? Does that make sense? So questions on that part? I'm just going to flip to see where we are. Okay. I'm not going to do any of the stoichiometry of titrations for the first test. So for the first test, things that I'm expecting that you should be able to manage is anything that we covered through the acid ionization lecture today. And then the one last thing that you might see is you might get a titration curve and asked how many protons are on it. That's it. Now, as far as practice for that test, that should be posted this afternoon. So you will have everything you need to practice for that test. There will be not only a bunch of questions, both in Alex and on D2L, and I'm going to eventually post them all on D2L just so you have availability on them. But there will be some in Alex so that you can, take a look at that. I am debating over whether or not your tests are going to be given in D2L or on Alex, because everybody else in the department has moved to giving them in Alex, and I'm getting a lot of pressure to do that. So they may get moved into Alex. So I will make that decision in the next day. And if it happens that way, you'll be expected to use Alex rather than the D2L. Now, the respondus monitor is the same in both. So be aware that that is the case. And I will have some things that you need to watch out for, especially if you're using a Macintosh. We've had problems with Macintoshes getting push notifications from like your phone and stuff like that. And that causing problems with the respondus monitor. So I'm going to be posting some stuff about how to turn those push notifications off, because if it boots you out of the test, there's nothing I can do about it. So you need to make sure that those things get turned off before you take the test. And then there'll just be some recommendations for, like where you should be sitting. There were also some instructions with the respondus monitor in terms of what you need to show me for the test, because I need to be able to see like your entire room that you're sitting in and all of the pages of your exam handouts to make sure there's something written on them that's not supposed to be written on them, and things like that. And I don't want that to take up test time. So I want that done in the check before the test starts. That way you won't lose any test time in doing it. But if I don't see that, that will be reason for me to question you on things. So during, especially for the first test, make sure that you follow those rules and showed me all the stuff that you're supposed to show me so that I don't have to question you on academic integrity. I don't want to have to do that, but we have to be careful with it. So things like you can't cover your camera, you can't sit in the dark, you need to be, you need to make sure that I've seen the calculator that you're using, just flash it at the screen, and your phone is not supposed to be where you are. So if you want to have your phone where you are, then I need to be able to see it, and it needs to be shut off. Okay? If it is turned on during the test, that is a problem. Phones are not allowed during the test. So, does anybody have any questions about any of that before we?
I deal with the Alex thing because it's like very specific, like as far as the answers go. Like, are you gonna go back?
So is D2L.
Okay.
So anything that gets done, regardless of where it gets done, you will be expected to turn in your scratch work, and that will be graded by me.
Okay.
Everything is very specific about how things get put in. Yes, but regardless, I will do my best to make sure that it doesn't auto-publish the grades, and you won't see them until I have graded them.
Okay. Thank you.
Yeah,
Either
no,
way, will the
Go ahead.
exam be open the 27th through the 30th?
Yes, the exam will be open the 27th through the 30th, and we will not have class on the 30th so that you will have time to take the test if you haven't had time to take it.
Okay, thank you. I had a question about the surveys that we're supposed to be doing.
Yes.
So we need to like fill out the survey, submit it, and then under assignments, like we upload a screenshot of which screen?
That's it. So it's here, let me show you. Where is my I've lost my mouse, sorry. So in D2L, if you go under more and you go to surveys, this is the page you should come to when you're doing them. After you've done one of these, so after you've actually taken one of these, and let me show you as a student. Once you've actually done one of those surveys, what it will show is that it says the name of the survey and then how many responses you have. So this will show that you've actually done it. The reason that I asked for that is because that way I can see very quickly that you've done that particular one, and I can
Okay, so
grade it
for
very
every
quickly.
survey that I do, I just take a picture of this screen and
Yes.
submit it? Okay.
Yep, that is correct.
Okay, thank
And
you.
I should have those all graded by like all the stuff that I have by Friday, so you can see accurately what your grade would be going into the test.
Okay.
Any other questions at this point?
Nope.
Okay. I'll do my best to get the recording from today posted as soon as it is processed. I will get those things that I owe you for answers posted in the next hour and a half, something like that. And then we should be good to go. So if you have anything that comes up between now and when you're done with the test, let me know. If you have any questions going through the test, you're not sure exactly what it meant, something like that, do the best you can. And then send me an email, tell me what your problem was. And you know, I mean, because you can't ask me questions. I understand that we may have issues with that. So that's not your fault. That's my fault. So we'll deal with that as the case may be. So, okay.
Sounds good. Thank you so
Awesome.
much. Hold on, can
Yeah.
we phone a friend during the test or
Uh,
not?
no, there is no phoning a friend. You may not use your notes. You cannot watch my recordings. Things along those lines. No, the respondents to lockdown browser rules are pretty clear. And you know, I mean, obviously, you're not supposed to have a tablet or any other computerized device with you when you take the test. If I see that, will be a problem. So,
Okay.
okay.
Sounds good. Thank you.
Awesome.
Are you employing
Thanks,
your
guys.
kids? Are you employing your kids for watching the videos or no?
So yes, I actually do that. I get my child to watch them the first time through, and anything that she sees that's a little shady, she's like, "Mom, come look at this." Okay, all right. So yes, I did. My child is 18. She does do that. So just so you know.
Sounds good. Thank you so much. Good to see you again.
Sure. And I will see you guys on Friday. So there will be class on Friday, even though it's not on the test.
Sounds good. Yes, ma'am. I'll see you soon.
All right.
Bye.
Bye, guys.
How do you do this?